Okay. So I'll try to do this a little quickly. There's a few equations in here, so you probably don't want to see them all, but I'll try to. I think some of them are worth seeing because of the underlying intuition in it. But basically, this is an idea that Art Lubell has published back in 2012. And the idea is basically that you use the second moment sort of information to as an IV for the endogeneity. I've not seen it used a ton in papers, but it does get used on occasion, right? So here's sort of a basic idea: is that we're going to throw out the intercept and we're going to think about sort of a mean-centered system. Simplifies this slightly, but it's not really that important. So here's a basic endogenous system. We've got some outcome y1, which is a function of x's, and some variable y2, which is likely to be endogenous, and y2 is also a function of the x's. And for the exclusion restriction, we want to think that one of the x's here is in this regression, but the beta for that particular x is 0. It doesn't belong in that regression, but we're leaving it in for notation purposes. It's not that important that you know that, but that's sort of how this is done. Lubell's 2018 paper is slightly different. But basically, we're going to now think about a couple of different assumptions. So some of these are fairly straightforward. We want x and y, xy1y, xy2y, and xx. So these are basically the moments of the data. X and y is the covariance between x and y, basically. xy1y is essentially the, how do I want to say this? It's the covariance between the sort of first stage and second stage. And x2y is sort of the opposite. And then we've got the underlying variance of the x's. So basically what we want is all of this to be finite, which means that we can't have any weird data. And we need it to be identified by the data, which basically means that we can calculate these means. These are very unrestrictive assumptions. We're going to make a couple of fairly straightforward moment arguments. This is then, we need the x's to be uncorrelated with the first term error and the x's to be uncorrelated with the second term error. At least that's what we would like, right? Because our endogeneity problem is with y2. Okay, so we want the x's to be exogenous, but we're not worried about what the endogeneity problem was with y2. Okay, so these moments are just statements about exogeneity of the x's. Okay, so that's not meant to be particularly problematic. And then you've got some z, which might be an instrument and is probably contained in x. We've got basically two moments of interest. One is that it is uncorrelated with the cross multiple of the two error terms, and the other is that it's uncorrelated with the variance of the error term. It is correlated, excuse me, with the variance of the error term. Okay, so where do these come from? Well, that we have to see because it sort of falls out of what's required to get estimates in this setting. Okay, so the first stage is identified. What's the first stage? That's this equation. That's not saying much. What it basically means is that the x's are, since the x's are uncorrelated with E2, I can simply run this regression. Right? This isn't saying a whole lot. And there's some z in that. Right? So I can get the pi terms without any trouble. It comes out as standard ordinary least squares. Okay. So these two moments are identified by assumption, and because those two are identified and they're finite, the pi term, which is the parameters are there, and the x's are uncorrelated with the error term, which also allows that pi to be unbiased. Okay, so that's the easy bit. I'm going to create two additional terms because it sort of simplifies the math. W1 and W2. W1 is a linear combination of E1 and E2, and then W2 is just E2. So the next assumption we're going to make is that we can find gamma. We can estimate it from the data, and we're going to make use of our sort of odd moment condition that Z is uncorrelated with the multiple of the two error terms. Okay. And so all we do is we rewrite those terms. So plug and chug some numbers. The covariance between Z and these two terms is basically the covariance between Z and these two terms, which we work out. It turns out to be essentially two covariances. I can always pull a constant out of a covariance term, so that's what we're doing there. Because by assumption that is equal to 0, I can find gamma by essentially rearranging and dividing this term by that term, right? So gamma, which is this linear combination of the error terms, the slope really, that is identified by the covariance between Z and these two W1, W2 terms, and then the covariance between Z and W2 squared. That's what's sitting in the denominator. For that gamma to be found, I can't divide by 0. Which is where this assumption comes from. W2 squared is essentially epsilon 2 squared. All right, by assumption. I've sort of renamed my terms. W2 is equal to epsilon 2. So writing this is exactly the same as writing the covariance of Z in epsilon 2. Okay? So those are the assumptions underlying the story. But once I have gamma and I have pi, right, because gamma is, right, gamma is the parameter on the endogenous variable. So I've got the first stage, I've got this parameter on the endogenous term. I get the betas by essentially subtracting this estimate from here and estimating a revised regression. Okay? So I can find the betas by subtracting off the estimated endogenous part and then estimating the revised term by this new set of regressors. Right? So it's sort of this three-step process, right? There's a first stage, and then there's this underlying covariance structure that I have to estimate, and then there's this third stage, right? So it's actually a three-step estimator, not a two-step estimator, which I've written, but it looks sort of like two-stage least squares. Right, so now I'll formalize that slightly to define the actual estimators. So here's beta and gamma. They are estimated by this thing inversed. You'll see this term and this term repeated. And now we're going to multiply it by these two components. This is essentially what makes up our instrument. Okay, and I'll come back to that, what it means in just a moment. Okay. So we can think through all of the different components and the proofs. I don't want to make this wildly complicated, so let me jump past this one. But basically, this shows us what we know about regression, which is that if we've got non-correlation between the error and the x's, we can easily get the estimator. Okay, it's not necessarily important, but it's relevant. The next part is trying to figure out what this phi zx term is, which basically requires us to multiply these things together, and all I've done is sort of rearrange those terms so that I've got an expectation, right? So this is now what I'm using essentially here to get this gamma part, okay? So this phi zx is sort of this z omega part, okay? And then I plug that all in, right? And there's lots of pieces. What we really care about is sort of this bit here at the end. I've got an expectation over x times x and y, and I've got an expectation over this deviation, z from its mean, okay, which I put in earlier. And then I've got 0 here, and I've got this covariance here. If I look at these two parts and I sort of multiply them out, by assumption, this term is also 0. So I am left with a very simple estimator here. I've got some matrix times the parameters is what I actually get in terms of expectation. And it's all built on this assumption here. Okay? So I'm obviously being a little quick given how much time we have, but well, we've sort of written it in a number of places. Here's what we're using for an instrument. So this idea is that if we have this heteroscedasticity in the data, right? So what do I mean by heteroscedasticity in the data? Here, I've got a variance term. And I'm saying that that variance is correlated with my instrument. Okay. So when I find, so heteroscedasticity is essentially this idea that I've got variation that isn't constant. Right? So here I'm saying it's correlated with some z. If z changes, then certainly we would expect the underlying variance to change, right? That's the sort of statement. So here is what I mean by having heteroscedasticity. In order to use this as an IV, I need a moment restriction, and this is the one that matters. I need Z to also be uncorrelated with this cross product of the error, and this is kind of a mathematical result, right? If this doesn't happen, right? If this doesn't happen, I can't use this heteroscedasticity term to get my estimator. I need some sort of correlation here, right? I don't want correlation here, but I use that to identify my underlying correlation. All right, so I'm allowing this to go away. I'm forcing it to go away because that allows me to identify the endogeneity term. Okay. Guess maybe I went faster than I needed to. So earlier this afternoon, I talked about a relatively famous paper with IV. So David Card, who fairly recently received the Nobel Prize along with a couple of other folks, has this famous work where he looks at IVs. All right, so it's a 1993 NBER paper that was later published, if I remember correctly. But the NBER paper is important enough. And here the question is basically, all right, well, we'd like to understand what college education might do for, for individual earnings. Okay, so we've got wages. We've got a series of controls like experience, race, SMSA is a measure of city size, south, right, in southern part of the U.S., where wages in general are lower, at least they certainly were back at that stage, and then marital status. He also includes experience, I do say experience here, right? The argument then is that education is endogenous, right? Whether or not somebody goes to college is not randomly assigned. People choose to go to college, or they have the funding to go to college, right? These are not entirely random events, okay? And so he suggests a couple of instruments. One is, well, they're both basically about location. Do you live close to 4-year or 2-year universities? So somehow we've got some measure of how far away they are from institutions, or how many institutions are within, a certain space from them, right? So this is a fairly famous instrument. And the idea is that, well, you yourself didn't really choose to live close to a university. Your parents might have, so there could be some endogeneity in there, but it's unlikely to be particularly massive. Okay. And so here are the different sets of estimates. All right, so with straight ordinary least squares, the college effect is about 0.07. So getting a college degree for this particular data set, which is fairly old data, college degree raises earnings by about 7%. That's argued to be biased, and the IV estimate is about 13%, which is nearly double, but right, massive increase, right? Look at the size of the increase in the variance, right? I said that this was what happens when you do IV. This is a great example of it. The standard error goes up 12 times. All right, this is a massive increase, a factor of 12. Right, so the t-stat drops from 20 to 2. Right, very big impacts of using IVs on this standard error. Approximately 2 times 0.05 is 0.1. So the confidence interval for the IV estimate is anywhere from 0.03 to 0.23. It's big. Right? And it certainly includes the ordinary least squares estimate. Another thing that I said earlier. Okay? And you see this often. Right? So it makes it also kind of hard to interpret, right? Well, the ordinary least squares estimate falls within the IV estimate completely. So is the ordinary least squares estimate wrong? I don't think so. Right, but when we use IVs and you read through David's paper, right, he'll say these kind, right, this is, we use IVs because we have to correct the endogeneity, and the endogeneity gives us this massively larger return on average, right, which is true, right? That's what the estimator is. On average, this is much higher than that one. But the space it covers is also quite a bit larger. So the second thing I did is I compared that. CARD doesn't do this, but I have CARD's data. It's widely available. I used this heteroscedastic IV thing where I used experience as the instrument. Now, and I didn't actually say this clear enough, so let me go back. You don't use experience. You use the standard deviation in experience. Sorry, not the standard deviation. Use the deviation in experience. So I can still include experience in the regression, but I'm also including a simple measure of error. I'm using experience minus its average as my instrument. Okay? So if I estimate that model, where experience minus its average is the instrument, I get an estimate of about 0.09, which is higher than ordinary least squares. I get a standard error that's actually smaller. Okay, so the amount of noise around this is a little bit better in some sense. But you also get, excuse me, you also get a smaller estimate. And it still certainly includes the ordinary least squares estimate. Okay. The second thing I do is I add Card's initial instrument into the model along with this Z minus its average, right? So I now have technically two instruments. I have the true instrument. Well, no, I shouldn't call it a true instrument. I have David Card's instrument, right? How many universities or whatever are close to me. And I've got this sort of experience differential also. Okay. And now my estimate is closer to 0.1. And my standard error actually drops a little bit more, right? This is the idea. Additional instruments tend to lead to slightly smaller standard errors, at least when I'm comparing these two and these two. I could compare either one of these two standard error-wise, because they both have 2 relative to 1. But you'll see from this, right? They're not. Well, let me rephrase. The IV estimate certainly contains in its confidence interval all the other estimates. Right? Certainly contains them all. The heteroscedastic IV and the heteroscedastic IV with an instrument certainly contains the ordinary least squares. Barely contains the IV, but does contain it, right? Because roughly 2 times this is 0.05, and 0.08 plus 0.05 is 0.13. So it is there. Okay. All right. So what do I want to sort of finish with? This is not counting the last 2 rows, right? This is a fairly famous paper that sort of shows the importance of IV. And how to estimate, sort of what you find. But the results are still, in my view, not wildly conclusive. Right? This one doesn't separate itself from OLS so much that I would say there's no way the OLS estimate is appropriate. Right. I can't, in my view, I can't reject the OLS estimate given the IV estimate. All right, and I think most statisticians would agree with me, but maybe I missed something obvious at some stage in a stats class. All right, I hope not. So, but the other thing that's, I think, kind of nice to see from this is that, I've got a different instrument and I've got a different estimate. Okay? That shouldn't surprise me given what we've said before, because the instruments are likely to work through potentially different channels. Okay? So I don't expect the same result. I don't get the same result. The other thing you see, as I said before, is that once I add an additional instrument, right? So you can think of this as being 2 instruments, this as being 1, and this being 1. Adding additional instruments reduces my standard error. Right, so this standard error is always less than those 2. Okay, so that also shows us some of what we've been talking about through all of those previous slides. Okay. And what I will do is post the code for this so you can just run this fairly quickly. It's quite easy to apply. All right, so you can do this with the LCS if you want, but I'll think a little bit more about that. I had thought about trying to bring out a few more things. I wasn't quite sure how much time we were going to have today, and a few other things. I think you have about 15, 20 minutes before you're supposed to be picked up. Does that sound right? Yeah. Okay. And where do you have to be? Well, not in 15 minutes. No. Okay. Unless you have a train that I don't have. Right. Okay. So, 5 days is a lot. This is a lot of material. Right? And I think when I first started studying econometrics, I think I was wildly more serious. Right? I kind of took these things at I was like, oh no, instruments. Even though all the other sort of theoretical stuff was known. And I still think instruments are useful. It's useful to see what kind of differences we get in estimates. But at the same time, I'm also not entirely convinced that you get a lot of mileage out of instruments. You don't always see, right, like in a case like this, big differences. And I made that comment about seriousness, right? I used to say things like, "Oh no, I've got the result now," right? And like I said yesterday afternoon, if you think you've got the right result, you don't know anything. Okay, we spend most of our lives sort of trying our best, doing our best to get as good a result as we possibly can, and sort of justifying it to the best capabilities that we have, right? And I think it's really easy to have a lot more faith in what you've got than you should have, right? Data's imperfect. The only thing we can believe probably is the computer, but we don't really know for sure about the data. And the assumptions across the board are really hard to fully believe, right? So you should always be a little bit skeptical that the assumptions you're making hold, right? I'm not saying you should never believe them. I'm not that bad either. I'm not that cynical yet, right? Maybe I will be in a couple of weeks. Ask me then. But today I'm not that cynical. So, have a bit of humility, have a bit of acceptance that maybe it's not quite right, and think about how other people might react to what you're showing them, right? Because at the end of the day, we're in this, I shouldn't use the word game on some recording, right? But we're actually in a game, right? And the game is doing the best you can and convincing people that you really put in a lot of effort, and you've pushed against the assumptions you've made to the extent that you reasonably can, and that we can believe that what we've got is reasonable. Not that it's right, I don't think. Some people probably still think what they've got is right. Like I said, I remain at least a bit more skeptical than that. There's tons more, right? This isn't even a large share of any econometrics textbook, right? It's like 4 chapters of maybe 5 chapters of Wooldridge. Right? We really haven't done that much, and you can't sort of how do I say this? You can't learn it all. There's more out there than you can possibly learn, and there are people building new stuff every second, right? At times it's frustrating. It's like, how am I supposed to know about that? The only way you can possibly know about that is doing something that's also very hard. And that is not so much reading everything you can, right? There's more produced in a day than you can possibly read. Don't ask ChatGPT to read it for you, okay? But find a couple of things you really find that you really like, that are really interesting to you, and dig in, right? Read as much as you can about it. See what people are using. See the arguments that people are using. Start to understand the arguments they're using, so that when you're writing a paper, at the very least, you can try to adopt or adapt, either one, right? The kinds of arguments that they're using, so that you can have the conversation in the language of the literature. Okay? And that's a really key point. Being able to speak like the people that are doing this and doing it successfully. If you can't do that, it's hard to convince the reviewers, who are all jerks, right, that you're doing a good job, right? Because you really are trying to sell something to somebody, right? And I can't tell you, right, I might be the worst salesman on the planet. If I had to sell stuff to survive, I'm thin already, right? But my God, I wouldn't exist, right? You wouldn't see me, okay? But that's what we have to do. We have to find ways to sell stuff to people, in particular, other economists, right? And they're some of the worst out there, right? They're real, well, I won't use the word. I'm being recorded. So, right, this, all you can in practice, right? See what happens, right? We've got the computing power to do stuff we didn't have when even I was in school, right? So you can simulate stuff, but of course you have to learn to simulate it. And you can imagine, okay, you can think, all right, so I'm making these assumptions. What happens if these assumptions get violated in a simulated sample, right? Okay, is that what seems to be happening in what you have, right? So you can make some of these kinds of arguments as well. So there's lots to do. There's lots to learn. This is 1 week of intense learning. I hope you learned something, or at least got interested in a couple of things, or whatever happened to cross your mind at the time. I actually enjoyed it. I only had to do a day. It's great. I feel a bit sorry for Matt, who did a whole heck of a lot more. But thanks for your attention. I hope you enjoyed and, like I said, learned something. And we'll see you somewhere at some stage. All right, cool.